Welcome to EDX Team EDS. In this session, we'll run through the mapping capabilities where you can put the power of modern phase mapping to work for you and change the way you do EDS forever. You may already be familiar with the general overall layout of the EDX Team software. And in this session, we're going to jump immediately into mapping by clicking the mapping button. When we make the mapping selection, it opens up other options available to us that are in the same context as our first choice for mapping. So we'll click on our next button, which is Image Area, to get the area from the SEM. And we could see that there are several choices associated with the image collection. Now we could jump into the mapping capability. Again, we see there are several choices available to us that are relevant to mapping. I'm going to stick with the defaults of the software and allow the system to automatically start the map collection with the default pixel resolution as well as an auto ID. You can see that as it collects behind the scenes, it assigns an elemental list. That auto ID assigns the element list, and then once it goes into the actual map collection, it compiles those elements together into phases. And what we see fairly quickly are the association of those elements together into unique phases. And as it's collecting, it overlays those phases onto the electron image, so very quickly within the first few frames we're able to see a clear distinction between not just elements, but all the elements in combination together. The Team EDS software has a unique interactive capability while mapping. So as we see the phases as we're collecting, we could also interact with those phases. By clicking on any one of the pieces of the phase pie chart, we see some information such as an area fraction ratio and the elements contained within those phases. And by clicking on a piece of the pie chart, we now see our elemental pie chart. In this case, I broke out the red phase and it tells me it's our calcium phosphate. And I break out our blue phase. Now we see the elements unique to the blue phase, so iron titanate. And as we click on the various phases, we get to see their unique elemental makeup. We can continue clicking on pieces of the pie chart, or we could always click on the map itself, and then it pulls out the elements contained in that phase. So here I'll click on the red area in our phase map, and it pulls out my red pie chart, and it pulls out or it displays the elements present in that phase. Of course, we could investigate even further by clicking on any element, and it will display that element from that phase. We see a very small amount of silicon and oxygen in that particular phase. But if we go to another phase, we could then see the elemental contribution, in this case silicon, from this phase, from the yellow phase. And we could see the various elements from that phase. And we could do that with any of the phases that we find from our phase pie chart. And of course, we could even take it one step further. So now, rather than just seeing silicon from this particular phase, we could click one more time, and now we see the overall silicon from the field of view. Same thing with iron. So iron from this phase, and iron from throughout. Oxygen from this phase, or oxygen throughout. Iron from the iron titanate phase, and iron throughout. In this manner, we could keep clicking on the different pieces of the pie chart to better understand the sample as we're acquiring. So we're already several frames into the map set, all the while we've been interacting with our data as it's collecting. So you see that we now collect with the default as a phase view, but of course we could always go to our display options and select a different mode of display, in which case now I'm going to go to the elemental display. And we see all of our elements broken out from the sample, and we could look at any individual element. Or of course, an elemental overlay. We could select as few or as many elements from the overall element list as we choose. And as we do that, we get a running overlay. And we could update and change as many times as we'd like. We also have another EDS unique feature, which is called our counts per second map. With the counts per second map, we're able to see the pixel intensity keyed to the count rate at each pixel. So the more counts that we get at each pixel, the brighter the intensity of that particular pixel will be. It means that the areas that produce the most X-rays will be brighter, and the areas that produce the fewest will be darker. This is a great way of seeing whether you have topography in your sample that might cause shadowing or shading of your data with little to no X-ray signal escape. That'll help you characterize your sample more. You could also see that various phases have different intensity or X-ray signal production. It's not always similar to a backscatter image. In some cases you have areas that, while they might have lower element or lower elemental energies, they will produce more X-rays. In this case, it's our calcium phosphate phase over here that produces a higher X-ray amount than the other areas. As we're collecting, we could also go back into our phase map and do some spectral analysis of each of the phases. So if we wanted to see the spectrum, for example, from the red phase, we just click on the red piece of the pie chart and we can expand the spectrum accordingly. The blue phase, we right click on the blue piece of the pie chart. And so on, with all the different phases that the system has automatically found so far. Another thing that we can do is visualize the sum spectrum, or the entire spectral count compilation of the entire field of view. And this gives us the ability to review the elements that it's found and to verify that the elements present are in fact the ones that we find to be correct. Of course, after the fact, you could always update your maps and your element list, rebuild your spectra, regenerate individual elemental maps. And a few of the other capabilities that we can do while we're collecting are shown here. So we could even assign elemental colors while we're mapping. If we decide that there are two elements that have a similar color, or that we would like to change the view of the element for any reason, we could just simply change it while it's collecting. As we're collecting, we can continue to investigate further. We see that there's one phase where it has two different phases assigned to it. So if we pull out the burgundy phase, we see that we have one iron titanium ratio And when we change the blue phase, we see we have a variation of titanium and iron ratio. This indicates that as we're collecting, the system detects slight intensity changes between the iron and titanium ratios that allow better sensitivity to better determine the presence or changes of the different phases within the overall area. I'll also note that we have drift correction capability as well as overall count rate drift. So we can monitor how much the count rate has changed throughout the entire map set. If we had a large fluctuation in count rate, this might affect our map from start to finish, and we can monitor it here. The smart drift correction capability allows the system to automatically choose a reference area with a high contrast and assign a refresh rate based on the actual drift that is happening in the system. At any time, we could go over to our environmental panel and check the conditions. So we see we're running at a count rate of about 55,000 with a dead time of 18%. And our microscope column, we've got 20 kV and 100x magnification. Of course, the bottom status bar allows us to see full details set up based on our user profile selections. And we can see the system performance, so count rate, dead time, and detector resolution of 128 EV at 50,000 counts per second and 18% dead time. We could stop this map at any time. We started it with a quality setting of standard. What the quality settings allow us to do is maintain consistent data regardless of sample conditions, operator, or beam conditions. With the selected quality setting, the system monitors the count rate and determines how long it would take to get a certain value or number of X-rays per pixel. In this case, it decided upon 76 frames at 53,000 counts per second. If we were to work at a higher count rate, it would be quicker or fewer frames, and if we were to work at a lower count rate, it would take a little bit longer. By keeping a quality setting consistent, operators working at different conditions can be guaranteed that they'll get consistent results. So I will stop this collection now. When I click it once, it tells me it's going to stop at the end of the frame. And then it automatically saves the data for me. And even though it's done acquiring, I can still interact with the data in the same manner as I did during collection. We now see that the data is saved for us automatically. When I click on Finish, I could then either pull up the map from the project panel or just go directly to Report. The system automatically creates a smart map template which exports all of the data into a report viewer. We see our phase map, our area fractions and the percentages of the various phases, as well as the pie chart, our conditions, and now we could see the individual phases and their quantitative values, as well as the individual elemental maps. From here, we could save as a huge variety of file types, most commonly PDF, PowerPoint, Word, Excel, or different images. When we save as any one of these file formats, anybody could access the data. In fact, the file formats will allow the individual objects, so your images, your spectra, to be remanipulated, so you could change the size and view of any of the maps or spectrum. We also have the capability to add more notes as well as search for any particular characters. In this case, I'll search for sodium, and it finds everywhere that we have sodium in the sample and highlights it for us. I'll close out of the report viewer now. If I want to get back to my results, I just go to the project panel, and it opens up all of the data from the map run that we did. So we have our various phases displayed here in outlined form. We have our pie chart that we could interact with. And we could continue to interact with our pie chart the same way we did within the mapping collection. When we pull out any piece of the pie chart, that particular spectra becomes highlighted by a solid fill. We could also get quantitative values for any of the phases just by clicking on the Q that's associated with the phase. And of course, we could save as an Excel file directly from here. Finally, we have many of our spectrum tools available to us, so we could update the spectrum accordingly. Finally, should we want to do any further analysis of this spectra, we could automatically load it within our analysis package. This will now conclude the Team EDS mapping capability. Thank you.